Hello, I wanted to go through our limiting and excess reactant problem, and I also wanted to do the complex empirical formula problem. We're going to do one at a time. This will be a really good review of stoichiometry. Really good review. So let's see what can happen here in this problem. We've got glucose, C6H12O6, plus oxygen gas. This is a combustion reaction. Notice oxygen gas plus a hydrocarbon. Oxygen may be present as well, as in this case. Whenever combustion happens, we're going to produce carbon dioxide, water, and these are highly exothermic, so we're going to get heat released also. Light released if it occurs explosively. We're going to start with 100 grams of oxygen gas and 0.250 moles of this solid glucose, this sugar. Well, by looking at this, we cannot immediately see which of these is going to run out first, so we will do a simple test. Let's convert the moles of glucose to, let's say, moles of carbon dioxide. Let's convert the grams here of oxygen gas to moles, and then to the moles of carbon dioxide. Just compare the numbers. The smaller number will be the limiting. The larger number is going to be an excess. Remember, once limiting runs out, product ceases to be produced. That's really important. And then there'll be excess reactant, which will be, all by itself. It has no partner to react with. Well, let's convert. Here's our 0.250 moles of glucose. Let's use the mole ratio from the balanced equation. Here's the mole ratio. For every 1 mole of glucose, I'm going to yield 6 moles of CO2. Mole ratio here. This cancels. Moles cancel. And notice we have 1.5 moles of carbon dioxide produced. Let's convert the grams of oxygen to moles. And then let's use the molar ratio. We see that 6 moles of O2 yield 6 moles of CO2. So let's convert grams of O2 to moles of O2 using the average atomic mass. Then let's convert moles of O2 to moles of CO2, and notice our answer. This simple and easy test tells us here's our limiting reactant and here's our excess reactant. Let's put a box around these, and then we can easily find this because I have a feeling we're going to need to use our limiting for some other questions. Determine the theoretical mass in grams and kilograms, moving within the metric system, of the carbon dioxide produced in this reaction. We need to use the limiting, so my little note here, let's use the limiting to determine product. Let's take a look at our amount of carbon dioxide that was produced when this much glucose reacted. We have 1.5 moles of CO2, and let's convert that to grams. So in 1 mole of CO2, there's 44.00 grams of CO2. Let's times these. Remember that, of course, is over 1, so we're just timesing that. There, moles cancel. We're left with grams. And when we do the math here, that's going to be 66.0 grams of CO2 produced. Let's convert that to kilograms. We know that there are 1,000 grams in 1 kilogram, which simply means we're dividing that value by 1,000, so we have 0.0666 0.0 kilograms of CO2. Put a 0 in front, and here is one of my answers. Here's another of my answer. Next, determine the volume of CO2 produced at STP, standard temperature and pressure. Well, let's save ourselves some work. We don't have to start from the beginning and keep working our way over. When we have work here that we can use, we know that this much CO2 is produced from this reaction, so 1.50 moles of CO2, and in 1 mole of a gas, any gas, at STP, it's 22.4 liters, and when we do the math, we're going to get 33.6 liters of CO2. Both of these are theoretical yield values. They're both theoretical. Anytime you do it on paper, it's theoretical. This is how much we should collect if we have perfect collection. This is the volume of what we're collecting, and that's if we're at STP, which would be 1 ATM, 1.0 ATMs, and 0 degrees Celsius. Of course, if you're at room temperature, if the temperature goes from 0 to 25 degrees Celsius, the gas is going to expand. But that's our value at STP. All right, I wanted to, for review purposes and for understanding the nature of chemical reactions and the balanced equation and the nature of stoichiometric relationships between reactants and products, I wanted to play around with this equation just a little bit so it's a good review and hopefully will lead to a deeper understanding of what's going on in a chemical reaction. Notice we're starting here with our 100 grams of oxygen gas, where we have 0.250 moles of this hydrocarbon compound, which is glucose. We're combusting it, getting carbon dioxide, we're getting oxygen, we're also getting heat. We've already determined that carbon dioxide is produced in this amount. Carbon dioxide is produced in this amount if we use the oxygen. So notice the smaller amount used 0.25 moles of the glucose, so there's our limiting. This much carbon dioxide is produced in moles. Of course, it's a simple conversion to go from that many moles of CO2 to grams, and it's a simple conversion to go from that many grams to kilograms, because again, 1,000 grams in 1 kilogram. And of course, down here, we've got our liters of CO2. Let's take a look here, and we know that this many moles of CO2 is produced from the limiting. So I've got that number. Let's put our moles here. It's very useful, beneficial to put moles underneath. Let's put gram or kilogram quantities on top. Be systematic. Don't be mixing these up. Let's look at the stoichiometric relationships here. I know that this many moles of CO2 is produced. I can use the stoichiometry to quickly tell me how many moles of water that are going to be produced. And there's our limiting. I'm going to put LR limiting because that's determining the product. Notice it is a 1-to-1-to-1 relationship between these. It is 6 to 6 to 6, but that's equivalent to 1 to 1 to 1. So we know, just by inspection, this many moles, if this many moles of carbon dioxide are produced, this many moles of the water is produced. And this many moles of the oxygen gas had to get consumed. That had to get consumed. And then this was completely consumed because this was limiting. Notice this is a 1 to 6 to 6 to 6 ratio. This is a 1 to 1 to 1. And is this the same ratio as the stoichiometric coefficients? Let's just see, don't even have to see. Notice if we divide 1.5 by this, that is the value is 6, so that is a 1 to 6 ratio. This molar ratio here is following the stoichiometric ratio, as it should. Well, let's figure out the gram quantity here. And we'll put the gram quantity up top. The molecular mass of glucose is 180.0 grams per mole. So 180. So I've got 45 grams, 45.0 grams. I'll put that here. How many grams do we have of each of these that are produced from the reaction? Remember, this is what... All right, I got cut off there, not quite sure what happened, but I think this is about where we were. I went through more work, but so I had to get a fresh, clean sheet and kind of start where the camera cut. We can see that here was our limiting reactant. Our limiting reactant is going to react and produce this many moles of product, this many moles of water. It's going to react with 1.5 moles, and we were making a point that this ratio of the reactant moles equals the stoichiometric ratio. 1 to 6 to 6 to 6. This is a 1 to 6 to 6 to 6 relationship also. Let's take a look at the mass. We know that in chemical reactions, matter is neither created nor destroyed. It just changes forms. So we had a certain amount of mass here, but we changed the mass, we changed the form of the matter to new chemical properties of water and carbon dioxide. Essentially, what's going on here is that the chemical bonds over here are being broken. New chemical bonds are being formed, producing new compounds with new chemical properties. Well, let's take a look at the mass. How much mass of water do we have? It's a simple calculation. We just convert moles of water to mass of water, and what we have is, it looks like 27.0 grams of water, just converting that many moles to grams. Let's figure out how many grams of CO2 we have. We already did that earlier, and I've got a fresh sheet of paper, so I'll redo it really quick. So 1.5 moles. We know that there's 44 grams in 1 mole. And again, we have that 66.0 grams. This total mass of the product should equal the total mass over here that reacted. We have 93.0 grams of totally new product here. New meaning water and carbon dioxide versus these reactants. Well, notice here, I've got 45 grams, and where did I get 45 grams from? I converted moles of C6H12O6 to grams of C6H12O6. All of that reacted, that's limiting. Notice when I add these numbers up, I get 145. So, Houston, we've got a problem. These numbers should add up, but maybe I'm overlooking something. I'm using 100 here, but not all of that 100 reacted. Some of this is left over. Well, let's see if we can figure out how many grams of this actually got reacted. I know that 1.5 moles reacted. I know that for a fact because that had to react with that many moles of the glucose. Well, let's see here. 1.50 moles of O2. We know that in 1 mole of O2, there's 32.00 grams of O2. So let's figure out the moles here of O2. So that's 48.0 grams of O2. This reacted. Well, let's go back to this number. Out of the 100 grams, 48.0 grams reacted. And let's add these numbers up now. And I'm going to get rid of that because that's not valid. And I'm going to go 48 plus 45 gets us 93.0 grams reacted. And that equals the mass of the product, the law of conservation of matter. How many of these out of the 100, it's obvious now, 52.0 grams are left over. So we had 100. 48 actually reacted with the 45 here. We have 52 grams left over. We produced this many grams of both of those products. I'm hoping this review is, it's meant to be helpful in the sense of putting some things together in terms of how the stoichiometry of the balance reaction relates to what actually reacted. These numbers that I wrote in were actually reacted with that amount. And of course, they're going to react in the same molar ratio as the balanced equation. Of course, once you have the moles, you can easily convert the moles to grams, like we did. All right. Thank you very much. I wanted to do the last in the series of questions about the limiting and excess and stoichiometric ratios, and here it is. We've got the actual mass recovered of the carbon dioxide, that's 60 grams. What's the percent yield? Percent yield is given by the actual yield, which is what's given here, divided by the theoretical yield. The theoretical yield we did, that's what our calculations are all about. In theory, we should get this much carbon dioxide. But we only recovered 60 grams. So we lost a little bit. It's not like that wasn't formed. This was formed, but we lost it in the collection process. So we have the actual yield divided by the theoretical yield times 100, and it looks like we're at a 90.9% yield. I also wanted to talk a little bit about sig figs. I am not going crazy with sig figs as I go through these calculations. What I will do when I'm finished with all my calculations, I'm going to go back to the original question, and I'm going to say 4 sig figs here in the oxygen gas, and I see 3 sig figs here. I'm going to choose 3 digits as my final sig fig answer, and then I'll go through and simply make sure that my final answers have 3 sig figs all the way through. It's that easy. As I'm doing calculations, I tend to not round off for sig figs with each calculation. I always keep more digits than I actually need in, ouch, that hurt, than I actually need in the calculator. And then I'll round off when I get the final answer. All right, so I'm going to go to the hospital, and next thing we do is this, that bad boy right there. That's the empirical formula problem. All right, thanks.